and you're ready to go. Enjoy your session.
Okay, well, we're on to the final session of Real World Crypto. I'd like to remind folks that in an hour and a half after these presentations, there will be a social. Please join it, even if you want to keep it quiet, keep your Zoom on mute. It's great to see everybody and have a farewell to what has been a fantastic conference so far. So right now, I'd like to introduce one of our invited speakers, Anna Lysyanskaya, who is going to be speaking about privacy-preserving authentication from theory to practice. So, Anna, please take it away.
Thanks. Just confirming that everybody's seeing the correct view, not the presenter view.
Yes.
Yeah. Triple checking. Okay, good. So thank you very much. So I'm going to talk about privacy-preserving authentication from theory to practice. And so before I get into that, let's just do a little philosophical digression on when you're online, what makes you you? So, well, what makes you you offline in general in life? So everybody knows the very famous quote from the mathematician and philosopher René Descartes, I think, therefore I am. So the way we can translate that to the online world is I log in, therefore I am. Of course, that comes with lots of disclaimers, provided no one else can log in as me. So then the question is, well, where are you logging in? And are you having a kind of an out-of-body experience? And the way that we typically conduct our online lives right now, we have cloud providers and they embody the entirety of our online life. So you just log into their service and they do the rest. And of course, there is another way of doing it, which is now popularly called self-sovereign identity, which means that no one can act on your behalf. Something like a cryptographic key is needed for that. And you don't need the help of a cloud service to make assertions about your identity. And you're the one in control of your personal data. So, of course, that's completely not a new concept, certainly not to this crowd, not to this community. It's just a new name for an old one. And I included a link to an essay where this term appeared for the first time. And, you know, the horror to an academic, this essay does not, in fact, cite what I think is the first very clear statement of this principle. Maybe not even the first, but certainly the classic. And the classic I'm referring to is David Chaum's 1984 paper, A New Paradigm for Individuals in the Information Age. And in it, David Chaum spells out a vision for giving individuals all the control of information about themselves, of their personal information. So I quote it from on the slide. You can see that I quoted from this article. And David Chaum is extremely explicit. The language he uses is extremely clear that his vision for how individuals need to handle their personal information pseudonyms when interacting with organizations. And then if they want to convey a piece of information about themselves, let's say one organization already knows it about a user and issued a credential to this user attesting to this fact about him or her, then you can see, he says, you transform a digitally signed credential received from an organization in a way that preserves the digital signature, but changes the pseudonym within the credential. So that's his vision for what would be a desirable state of affairs. So this self-sovereign identity notion is not a new concept, but maybe the world is finally ready for it. And we don't even need to look very, very far. As I was preparing this talk, the New York Times helpfully gave me this headline about Tim Berners-Lee Lee's efforts to bring this about. So this, just look at the headline. He created the web. Now he's out to remake the digital world. Tim Berners-Lee wants to put people in control of their personal data. He has technology and a startup pursuing that goal. Can he succeed? So this, this was at the top of my New York Times feed. So maybe the world is ready for this ambitious vision. Would be nice if they cited Chaum. So in our meme-enriched world, here's the meme, self-sovereign identity. How it started, David Chaum had this vision of conducting all of our affairs in a privacy-preserving way that gives individuals control. How it's going? Well, it's not. It's right now there's talk of maybe using at least cryptographic credentials worldwide to, for example, convince verifiers that you've been vaccinated from COVID-19. Note that this in this particular meme, the credential that you're seeing on your screen is not privacy preserving. It's just a QR code, but at least it's a cryptographic signature that you may or may not choose to show somebody. And this is actually a mock-up from a project that I am contributing to that has to do with MIT. If you're interested in, the conversation on how digital signatures and cryptographic credentials can help bring about some kind of a vaccination credential in real time, let me know. Anyway, so what's underneath this this vision of self-sovereign identity? So of course there are cryptographic foundations, and if we forget for a moment about the privacy-preserving case, the cryptographic foundation is fairly straightforward. It's just a digital signature scheme, and we've known how to digitally sign for a long time, which is why I put some old pictures here and also some maybe more recent pictures. So these are all familiar faces, Diffie and Hellman and Ralph Merkle and RSA, and of course, GMR, Goldwasser, Micali, and Revest formulated the actual definition of security for a digital signature scheme. And anyway, so we understand what a digital signature scheme is, what it can do. We have many candidates, we have many standards. So if you don't care about privacy, if all you care is just giving the individuals the ability to present information about themselves in a verifiable way without relying on some third party certifying that the information is accurate, digital signatures allow us to do this. Now, if you care about the privacy preserving case, now we get, as far as theoretical foundations are concerned, things are much more, there are very rich tools that come into play, such as zero knowledge proof systems and secure two-party computation. And let me show you what I mean. So these tools that underlying the suite of cryptographic techniques known as anonymous credentials. So what's an anonymous credential? So let's say that you have a user who cares about his privacy and you have a verifier. And the user wants to gain access to whatever resource the verifier is controlling. And the verifier doesn't want to just give anybody access. It wants to make sure that you satisfy some whatever access control policy the verifier has. So he's going to say, well, who are you? And of course, this user can say it's Bond, James Bond. But remember, he cares about his privacy, so he's more likely to say, I can tell you, but then I'll have to kill you. So maybe the problem is that the verifier asked the wrong question. So in a second iteration of this interaction, he can try to say, okay, I don't care who you are. All I want to do is I want to see your certificate. So show me your certificate. And the user might say, okay, here's my certificate, number 007. But remember, this is a privacy conscious user. So again, he is probably more likely to say, I can tell you, but then I'll have to kill you. And why is that? Is because a certificate, if you keep showing the same certificate everywhere you go, it's linkable. And so you reveal information about So as you keep using it, you reveal a lot of information about yourself. Eventually, you're not anonymous at all, even if the certificate does not explicitly have your name on it. So what the anonymous credentials allow you to do is to instead answer, sort of showing the credential in the clear, the certificate in the clear, you convince the verifier that you're authorized without revealing any other information. And that's called a zero knowledge proof, those of you who don't know. So what's underneath this, what's under the hood here, is a cryptographic commitment scheme and a digital signature scheme. And there are 3 protocols that are necessary for this vision to fit together. There needs to be a robust, and by that I mean fairly efficient, zero knowledge proof of knowledge of equality of committed values, secure party protocol for signing a committed value, and another robust, efficient, zero knowledge proof of knowledge of a signature on a set of committed values. Okay, are you with me? Hope you're still with me. This medium is a little bit hard to gauge whether people are with me or not. So what do I mean? Why do we need these building blocks? Well, here is what's kind of happening here. When the user wants to convince the verifier that he does have a certificate, he conducts a zero knowledge proof. Here's a commitment to my identity or secret key, and here is a zero knowledge proof of knowledge of the CA. This is kind of a mutually trusted entity, that the CA has signed whatever's inside the commitment. And maybe the verifier doesn't just want a certificate from the CA. Maybe in addition, the verifier wants a certificate from another organization, such as the IACR. So then we're going to have 3 components. There's a commitment to my identity or secret key. There's a zero knowledge proof that the CA has signed the contents of the commitment, and there's a zero knowledge proof that the IACR has signed the contents of the commitment. And there's, of course, a lot of awesome theory stuff that makes all of this possible. So there's nice cryptographic commitment schemes that lend themselves to these types of protocols. There are specific signature schemes that work with them. And a lot of this is stuff that I've worked on. There's a signature scheme that's based on strong RSA. There's other signature schemes that are based on a bilinear setting. There's structure observing signatures, etc. And there are lots of other additional features. So this is where I am, because this is Zoom is a weird medium, and I don't want you to have sensory overload. I'm gonna just talk through the features, and then I'm gonna flash the slide with more words, so that when, if in case anybody wants to play back this talk, you can pause on the slide with more words. But first, I'm going to talk through it, and then I'm going to give you the words, so that because the human brain can only process one thing at a time. Either you're reading or you're listening. So I want you to be listening, and then if you need to read, I want you to pause and read if you want to. Okay, so what are the additional features in this framework? So you can incorporate attributes into credentials, such as, for example, date of birth or geographic attribute, and then you can disclose them or not as you wish, or you can disclose some property of your attribute, such as, for example, the expiration date can be an attribute, and you can disclose that your credential hasn't expired yet. Another feature is your credential certificates can be limited use. So you can use it, let's say, if it's an electronic cash, electronic wallet, you withdraw $10, and you can spend them one by one anonymously. But once you've spent all 10, you're done. So that's limited use, how many times you can use. Or you can have e-tokens, which is limited use in the sense of how frequently you can use it. So for example, if it's a newspaper subscription, perhaps it allows you to read up to 100 articles a day. But if you try to download more than that, that's outside of your subscription terms. So you cannot do that anonymously. So that's the sense in which you can limit how these credentials are used. Then there's something called ID escrow, which means that you are pretty much anonymous. Your privacy is pretty much respected, but in some transactions, you might reveal the encryption of either your identity or of some of your attributes that can be decrypted in case of emergency. And finally, a very important feature is revocation. So now I'm going to flash the slide with the more words, but I'm not going to read it. So this is for playback, for the purposes of playback. So this is my slide with more words. So all of these features, the reason I covered them is because they're helpful when we want to think about, anonymity online is a little bit of a Pandora's box. And there are some arguments that one might make against using anonymous credentials, against being anonymous online in the first place. And those arguments are, so specifically for credentials, is that anonymity is an invitation for abuse. For example, Alice will share all of her credentials, so it's no longer meaningful. Like, this credential is no longer saying this is an authorized user, because she might share her credentials with all her friends, and now they're not authorized users anymore. So there are answers to those questions that take advantage of those features that I just went over. So first of all, anonymity is not the issue. Any online credential is going to have this possibility of being abused this way. Secondly, this is where limited use credentials can help. So that's a useful feature for not abused. So revocation of credentials, if you're abusing your credential in the anonymous case, you can be revoked just as well as in non-anonymous case. And same, and you can escrow Alice's identity. So if something goes wrong, you can find out who she is or whatever it is you need to know to take action. You can make her key too valuable to share. You can also tie her secret key to some hardware so that it's not easy to share. So all of the stuff that I just went over, it isn't, it's by now quite old, and a lot of it has been implemented. So for example, direct anonymous attestation was adopted more than 15 years ago, and it uses these elements that I described in order for to attest to remote parties that your machine it has this TPM, is enhanced with a TPM. Then there's an implementation that Jan Kamenisch and his group at IBM, IDMX is the implementation of CL signatures and various optimizations and features. So a lot of what I covered is part of the IDMX implementation. And what isn't part of IDMX is part of a project which is a consortium of many companies, the Hyperledger Consortium. They have Hyperledger India and Ursa implement these things. So there's code for this, and also academic grade implementations and other efforts. And of course, I'm speeding up because I've only just barely covered the intro, and I haven't quite gotten to, and I'm only now finally ready to get to the punchline of what I actually want to say. So, all right, so let's get to the punchline. So the next question is, what's been standardized? So why are standards important? Well, they're important because if you want something used in practice, you need to make sure that people understand how to use it. There's interoperability and shared understanding. And there's the same API across different application scenarios so that people can use it without understanding all the crypto, all the details. So what's been standardized? And now you can throw tomatoes at me because what's been what-dized? These are our, if you're going to throw tomatoes at me, I require organic local tomatoes. So that's what you're getting in this picture. And don't stop at tomatoes. You can also throw some eggs at me, because I think that the way that we cryptographers think about anonymous credentials, and this introduction that I just gave you into anonymous credentials, is too complex for a reasonable standard. So all this stuff that I just covered, and I covered it in as high level as possible, and I tried to make it simple, but it's too complex for a reasonable standard for somebody who isn't a cryptographer. to understand what in the world I just talked about, and make a yummy dish out of these tomatoes and eggs that you just virtually threw at me. Let me be more specific. What I mean is that it would be nice if we could explain this privacy-preserving authentication, anonymous credentials, without requiring that our listeners understand very complicated technical notions such as cryptographic commitments, zero-knowledge proofs, and security party computation. And we want to create APIs that match this understanding so people can use it without having to get into the weeds every time that they use it. And it would be nice if we could do this by building off of intuition that developers already have, hopefully, at least the ones that work in this area, about standard digital signatures. So, okay, so what's in a name? So we all know what anonymous credentials mean, but by any other name, they would be as sweet. So let's experiment with giving anonymous credentials a different name. And I want to build off of this other construction, and that's a fairly recent terminology called Mercurial signature scheme. So what's a Mercurial signature scheme? The name comes from my paper with student Liz Kreitz. I just happen to love working with people whose name starts with C, last name starts with C. And it's an extension of something called structure preserving signatures on equivalence classes that comes from a paper by Fogsbauer, who's H? My bad. I'm blanking on the H. S is Slamenik, from a few years ago. And the idea here is that what gets signed is not just a single message, but it is a representative of an equivalence class of messages. So if you have intuition for what a signature scheme is, what a digital signature is, then this is just a slight extension of this intuition. So what's being signed is just a representative of an entire equivalence class. So once you get one signature, you can kind of translate it become a signature of a related message. And also under what public key? So it's not just a single public key, but it's a representative of an equivalence class of public keys. So you can, if you have a signature under one of the public keys, you can transform it into a signature on the same message, the same class of messages, but under a different, an equivalent but different public key. So why is that helpful? Well, let's say that we have a user who goes to this verifier. The verifier says, "Show me your certificate." And the user says, well, he cannot say, "Here's my certificate number 007, because remember, that's linkable. So instead, he uses this equivalence class notion in order to find another representative. So instead of just having one certificate, he has a whole equivalence class of certificates, and he gives the verifier a representative of that equivalence class. And if you want it to be privacy preserving, we want to make sure that it is hard to determine whether two certificates belong to the same equivalence class. So now we're using language that doesn't include things like commitments and zero knowledge proofs, but we're describing the same exact privacy requirements. So how does a Mercurial signature help here? Well, let's say that we've established that this certification authority's key is this PKCA. The user says, my public key is PK sub-user. My certificate is the CA's signature on my public key. Now we can use my public key for whatever it is we need to use it for example, for TLS. And next time I go to the same or different verifier, I provide a different public key that is equivalent, PK prime for the same user. And I compute for this different but equivalent public key, I compute a new certificate, and I show that to the verifier. And I could do that again. And also we can include some attributes, some identity attributes. So here by I mean an encoding of attributes. So maybe my signature is not just on my public key, but also on my attributes, on an encoding of my attributes. And I can show that, and maybe I can do some selective disclosure on these attributes. So to dive a little bit into this Mercurial signing business. So what gets signed in the anonymous credential is a user's public key, and it maybe let's say that that's known to the signer who's signing it, and an encoding of this user's attributes, and possibly encodings of some keys for conditional anonymity and revocation. And so this notation enc data, let's have it mean the encoding of all this data, so all the attributes and keys. So the encoding of your public key and the attributes and keys. So what gets signed is an encoding of all this data, and the signer doesn't necessarily know what this enc data is an encoding of. Perhaps there's some selective disclosure on that. And what do I mean by equivalence classes of public keys? Well, potentially two public keys can be equivalent if they have the same underlying secret key. And in existing anonymous credential schemes, it's usually pretty straightforward to see what that would entail. And equivalence classes for what is signed, for the messages that are signed, if we're signing a public key and data together, then two messages that are signed are equivalent if the public key components are equivalent, and if the enc data is the encoding of the same data. So with that, this hopefully makes sense. So when the user comes to convince the verifier that he's authorized, all he needs to do is he just picks another representative of his certificate. So here is kind of a little bit more of the input-output specification. And since I'm low on time, I'm not going to spend a lot of time on this slide. So this is another slide where you can pause it if you're viewing it as a recording. But the point is that if you are if we're doing a Mercurial signature, we can break up the signing algorithm into a pre-sign. So that's the part that you do with the signer, and you get some kind of a pre-signature S. And then this pre-signature S allows you to compute an actual signature on any representative of your message class. So once you have just a signature on your message M, and there's some auxiliary information about this M, then you can transform it from this S. You can compute a signature on any of the messages in your equivalence class, meaning that you can get a certificate on any representation of your public key and an encoding of the same attributes that you got. And then the verification algorithm, just a standard signature verification algorithm. And then optionally, this is part of the definition of a Mercurial signatures. But for this way of thinking about anonymous credentials, this is an optional component where you can convert a signature from one public key to an equivalent public key. Okay. And the signature scheme needs to satisfy security properties that are very, very similar to just standard signature scheme. So correctness is exactly the same. So verify needs to accept things that are correctly computed. And unforgeability is very similar. You have an adversary who can query the signer for messages of his choice, and he gets these pre-signatures S2. And then when he's done with that, he wins if he can output an equivalent public key to the one under which he was challenged, and a signature on some message M that isn't equivalent to any of the messages that he queried. And of course, it's class hiding. So this other very useful property is that it is impossible to determine whether a pair of messages come from the same equivalence class or a pair of public keys do. So that's what gives us the privacy. So if we recast anonymous credentials in terms of Mercurial signing, then we can piggyback off of people's intuition for signatures and for what equivalence classes are. And this part, so these first three parts, the setup, the setup, key generation, signing algorithm, verify, all existing anonymous credential constructions already do this. So now we don't have to talk about zero knowledge proofs. Now, convert sig is very nice if you want to also allow for delegatable anonymous credentials, which means that the user doesn't get a certificate directly from the top. There's some chain of command, and each link on the chain of command can use their credentials to delegate capabilities to the next link in a way that is privacy preserving, as in when you get a credential this way, you don't need to know who issued it to you. You just know that they are authorized and that you got a valid certificate.
Hi, Anna. Sorry to interrupt,
yep.
but we're 1 minute left in this talk. We're a little
okay, good. So I guess I had a little bit more to say about delegatable credentials, but hopefully, if you're following so far, now it means that the user has a credential chain that goes from the CA to the first to the first person on the chain of command, to the next one, to the next one. And if he has such a credential chain, he can just pick another representative of the same equivalence class of credentials, of certificates on each link next time he goes to a verifier, so he can be unlinkable. Okay, and another real world application of this delegation, and that's actually something that I'm doing together with a company that I'm involved with called Gradient Technologies, is you can use this to secure the to secure applications as they are running on your computer or your device, because what you can have is you can have a boot. If you have every link of what's happening on your device endowed with a public key, so you have a bootloader that boots your operating system, that in turn calls an app, and an app wants to certify some data. If your device is authenticated by some certification authority, then you can have credentialed on every link of this attestation. And so you know in the end that the data that comes out of this machine, you can have some confidence that it comes from a machine that has been that's like certified by some manufacturer, for example, that is running proper bootloader, that loaded the correct version of an operating system, not some hacked operating system, and in turn the operating system is running an app that it knows what the app is. It's not some rigged app, and the app has certified the data. So this is a work in progress. So now, just to kind of sum it up, why I'm talking about Mercurial signatures, this is without convert sig. This is just a renaming of anonymous credentials, and there are a lot of candidates of implementations. And with convert sig, you get these other cool things that you do with delegation. And we can do actually much better, because unfortunately, our existing Mercurial signature construction with convert sig, we can probably get much, much better constructions. And I won't get into detail. So the conclusion, so this is what I really want to say, is that we have these wonderful foundations and really powerful building blocks that allow us to get anonymous credentials with all kinds of cool features. But what we need is a formulation of anonymous credentials that has the right level of abstraction. And maybe Mercurial signing is one such approach. And there are a lot of open problems, and I'm looking for PhD students if you're interested in working on this. And there's actually a lot of work to do for industry as well, in kind of bringing this vision to fruition. And I would love to talk to you if you want to take part in that too. And in particular, you know, if you are looking for something something exciting to do with this AHA framework with the Gradient, I would be very excited to talk. That's it.
Okay, thank you so much, Anna. We have a lot of questions for you in the chat, but
wow, okay.
For time, we will be moving on with the program. Thank you so much.
Oh, oops, sorry.